In order to understand these concepts a little more clearly, let's refer to the diagram of the microscope that we have on the screen. Here you see the compound microscope with the transmitted light illuminator. So we have a tungsten halogen bulb in the transmitted light illuminator that sends light through the base of the microscope. Here you see it traveling through the field diaphragm. And remember that the field diaphragm is the diaphragm that we can close down and see it in the field of view. That's why we called it a field diaphragm. The light then travels through the field diaphragm and is reflected off a right angle mirror, and it leaves the base. It leaves the base of the microscope, and now it travels into the condenser. Remember, the condenser is an optical device that condenses the light into a small cone of light so that it can travel through the specimen, which is here on your XY stage, and into the objective. In the objective, all of the useful magnification takes place. This is where all the high-resolution images are formed. Those images are then projected through the nose piece and through this vertical illuminator, which we'll talk about in a second, and into the binocular or trinocular tube for the observer to see. So that's transmitted light. Now this microscope also does reflected light. Remember, in fluorescence we're using reflected light to illuminate our specimen. So this is the fluorescent vertical illuminator. Here we have the lamp housing, which has that mercury bulb that we're going to discuss more in a few minutes. It produces a lot of light which travels through the vertical illuminator. Here you can see it traveling through a field diaphragm. Again, we can close this diaphragm down and align it for alignment purposes. The light then travels through what we call a barrier filter, an excitation filter that produces the light, that blue light that you saw in the microscope, to excite our specimen. Now, a lot of specimens will autofluoresce. You can excite them with a bright light like 490 nanometers, and they will automatically give off light or emit light. That's called emission light. Usually the emission light is a longer wavelength than the excitation light, and we'll talk more about that later. So the light travels through this excitation filter, reflects off of a mirror, and is sent down through the objective to impact our specimen. So we're reflecting light off of our specimen. Now the light that is emitted from our specimen travels through the objective, through the nose piece, through the mirror, and up into the trinocular tube where the observer can see it, or we can record it on film. That's reflected light fluorescence microscopy.